It turns out that not every language is regular. We expect that, right? If you have something called a regular language, then you expect that there are non-regular languages as well. When we talk about how to find out if a language is regular or not, we can come up with a regular grammar, but maybe we don't. Like, our failure to come up with a grammar doesn't mean that it's not a regular language. It could just mean that we are not clever enough to find the grammar. There's something called the pumping lemma, which says that if you have a regular language, then there has to be a cycle someplace in the DFA that represents it in order to recognize it, if it's of significant length. So if we're talking about a regular language that allows an infinity of strings, we can only have a finite number of states. We can only have m states. There has to be someplace, if the string is larger than m, right? Any string in this language that's larger than m has to repeat someplace inside the machine. That's just how nature works, right? This has to happen. This is called the pumping lemma. That someplace here there has to be a state that's reached multiple times, because there's more elements in the string than there are states. For a finite regular language, that doesn't have to be the case. You could have a state machine that's 100 states, and if every string in the language is less than 100 elements, then you don't have to repeat at all. But for an infinite regular language, then you have to repeat at some point, because our state machines are finite. There's only so many steps in the DFA. So one thing that we can do to determine if a language is not regular is to show that this property doesn't hold. That because there's this loop here going on, at least one place, it actually can produce a string that's not of the language. Here's some more math words down here to kind of identify this idea. But I will ask you to do a sort of a proof of this for the assignment, but we're not going to get too deep into this. So I'm not going to go through all of this. This is basically just saying that this is how mathematicians would phrase this for setting up this idea. You basically say, let there be this string in L, and then you know that this pumping property exists down here. This is really important, the pumping property. X, y to the k, z. X is some sort of sequence through the path. Then y is going to be what we call the one that repeats, and then z would be the rest of the sequence. So basically we have to identify, if something's a regular language, that there exists at some point this repetition. And what we're going to say here, the way we do these proofs is by contradiction. We just assume that this exists, and then we can show by manipulating the symbols around that this structure is going to create something that's not of the form of the language that's given to us. Here's an example. This is the canonical language that is used to show something is not regular. This is the first non-regular language that we've seen. And it's really instructive to spend some time thinking about this. You should look at this language and try to come up with the DFA for it. Pause right now and try. I'll wait. I guess if you're pausing, I don't really have to actually wait, do I? All right. In any case, we have this, the problem here is that we have n 2 times. So you can do this a to the n. If it's just a to the n, you're good to go. There's not a problem at all with it, because you just have the state go in and you can repeat the a n times. And if this were a to the n, b to the m, that would be fine too, because you would have your state for a, your state for b, and you would just loop back to them a times and b times. The problem is forcing the b to happen exactly the same number of times as the a. What you have to do is remember how many times the a cycle went. And our DFAs have no capacity to do that. Our DFAs have no memory. They're a weaker model of computation than one that does have memory. We're going to talk about this. 2 videos from now, we're going to modify our DFA, add a memory to it, and then we'll be able to recognize languages like this. But so far, we can't do that. And this language here tells us why. So it's really helpful if you go here and you try to come up with your DFA for this, you'll understand why. So if there's an n and an m, it's possible. But if it's 2 n's, it's not possible, because there's no way to know on the second b exactly how many times. For a fixed n, sure, if you just replace these with 5s, then fine, just 10 states and you're done. But this is saying n can be any natural number. So this would be things of the form AABB, AAABBB, AAAABBB, not just a fixed n, but any sort of string that has the same number of a's and b's. And there's no possible way using a DFA to check for that, to accept a language of that type. So we can show that now using the pumping lemma. So we assume by way of contradiction, right? This is using our IP rule. So this is going to be really fun for you because we've been doing all these formal proofs, and here's an informal proof. We want to assume that it's a regular language. This is powerful, right? Maybe we appreciate contradiction proofs more now because we've seen what happened in the formal logic where when you get to use your IP rule, we get to add a premise to the system. And that's exactly what you do. This is why contradiction proofs are so powerful, because we get to assume that L is regular. And now we get to use all the powers of regular languages. We get to just bring in all that stuff. Because it's infinite, the pumping lemma applies. It's an infinite regular language. So now we choose a string, A to the M, B to the M. So we just pick one of the strings from this language. Then this is the pumping property up here. Then S has to equal X, Y, Z, where Y is not the null string. And XY itself is less than or equal to M. And so this is now have to be in the language for all the Ks. So this type of thing has to appear everywhere. And when you run through the math, what you end up with is this kind of thing here. We try for a contradiction with K equals 2. So this is all the setup. This is the form that these proofs take. We set this up here. You write a line like this, and then we use this. This is just based on the form. So this S equals A to the M, B to the M. This comes directly from the form of the language that we're given. And then all of this stuff here comes from applying the pumping property. And then what we do is we try for a contradiction. We just say K equals some number. And this can be whatever, right? You might find a contradiction at 2 or at 3 or at 4. And then we just say that, okay, so now we have to have X, Y squared, Z. But this means that you have A to the M plus I, B to the M, which is not an L. This isn't a string. This means that this, if it's a regular language, we've assumed it's a regular language. So therefore, this string has to be an L, but we know it's not because L doesn't support strings that have different numbers of A's and B's. So it's a contradiction. So we've derived false from A, derived false, not A, right? What's not A? L is not regular, QED. This isn't easy. This isn't obvious. The more mathematical background you have, the easier you can just read through this. There's examples in the text. You can pause here again and read through this text here and try to get it. Again, it's in several parts. The first part is the assuming it's regular, a pumping lemma applies. Then you pick an S that's of the form of the language you're given, and then you can say that you use the pumping property, and then you say that you relate this A to the M, B to the M to the X, Y, Z. So X, Y has to be a string of A's in this case, and Y is A to the I, and you just work through this. But the intuition that you have, the intuition for this, is that you try to write the DFA for this, and you see it doesn't work. And you see it doesn't work because of a lack of memory, because we can't tell in the DFA construction that there's the same number of A's and B's. One more example here. This language is more complex. It's got some A's and an A here, but those don't really matter, right? Those are just individual jumps with a state. The big thing here that makes this non-regular is that I have a B to the N and a C to the 2N. So I have exactly twice the number of C's as I do B's. So anything that has a couple A's in those positions and then twice the number of C's that I have B's, that's going to be something in this. And again, the reason this is non-regular is because this relies on memory. This relies on us knowing how many times we found the B before we get the C. It doesn't matter if it's 2 or 3 or 4 or the same number, right? C is a function of the number of B's. The number of C's is a function of the number of B's. And so the only way this can possibly be done is by augmenting our DFA with memory. And that's what we'll do 2 videos from now. We'll introduce a new kind of finite automata that will be able to handle this, but a DFA can't. Regular languages, the idea of a regular language, a regular grammar, a DFA, they're not powerful enough models to support languages that are this complex. This is a much more complicated theorem. I don't really going to go through every single step here. You have it on the screen. You can look through it. Again, there's examples in the text. There's a problem in the text too that has some of the bold-faced ones, are solutions in the back of the book. So you can kind of pattern match, kind of get a sense for how these work. I'm just trying to hit the high points. There's really no substitute for you reading through and spending time with this. And again, it's about spending time with the idea of a regular language. If you can really identify, if you can really use this pumping lemma, not necessarily generate a proof of it, right? But let the pumping lemma inform your intuition about why this is non-regular language. If you can say this is non-regular because it requires memory, because it requires that. And then if you can understand how the pumping lemma works, which is sort of basically saying that. The pumping lemma is a mathematical way to say it requires memory, because it's using contradiction to say that, oh, well, I know it goes this many times, and then there's no way to know over here. It breaks the pattern, right? The pumping lemma is always going to break the pattern. So like, look at these cases down here, right? All of these things that are being brought up here are breaking the pattern of C being twice the number of times as B. That's the whole point of the pumping lemma, is to break this dependency for one symbol on another, the number of times it's going to be available. So the pumping lemma works directly towards that. We can say informally that we don't have memory, and so if we have any letter in here that is dependent for its number of times appearing on the number of times something else does, then that's not going to be regular. But to get it a little bit more mathematical, not quite formal yet, right? This is all informal. This is all an informal group. But to say it a little bit more mathematically, we can come up with a pumping property, and we can use the pumping lemma in all of these sorts of things. So that's really the idea here. The most important takeaway is to be able to, in just normal English, talk about why some languages aren't regular. You should be able to look at them and just kind of get an intuition about it. And that's why we do this. In mathematics, we try to build up our own intuition about things. We have a great intuition about the physical world, for example. We run and we throw balls and we dive on the ground and we roll around and we understand how physical things work. But we have no intuition at all for mathematical objects. The only way we gain that intuition is by spending time with them, by proving theorems with them, by working with the definitions, by doing this sort of thing. So it's not really the outcome of this that's important, just like it's not the outcome of throwing a ball and having your friend catch it that's important. But it's just the intuition you build up for how the physical world works that helps you navigate life in a physical way later on, right? All the play you do as a child, none of the output of any of that was important at all. But it's the skill that you gain just being able to tumble or being able to exist physically in the world that helps you. That's the exact same thing that happens mathematically, but we have to spend time with these ideas. And we don't get to go run around and play cops and robbers or something to do that, unfortunately, right? We have to actually sit down and work with the mathematics. So you have to spend some time on this to understand it. The big takeaway, again, is not being able to do a proof super fast or super well. It's understanding that not all languages are regular, and what is the limitation? What is it about the DFA that limits it? Because we're going to break that limitation. We're going to remove that limitation and come up with more powerful state machines. Those won't be super powerful, right? There's still going to be limitations there as well. So every model of computation that you come up with, every model of computation that exists, we're going to want to be able to say, hey, what are the limits to this? What kind of languages are not recognized by this? And by studying the limitations of regular languages and DFAs, we get closer to that goal.